And very roughly speaking, fission is the process by which you have a collection of bound neutrons and protons that splits and releases a lot of energy. For the funding sources, it's important for nuclear energy and global security. From the more fundamental point of view, it's relevant for nucleosynthesis, so the creation of elements in the universe. And the problem itself is just interesting. It's interesting because it's been around since 1939, but we still don't have a complete description. And I'll try to explain why that's the case shortly. Just one line that's going to summarize the key idea behind fission theory is you want to try to, as a community, we eventually want to have a predictive theory that can describe fission for all relevant observables they can measure experimentally for all nuclei across the nuclear chart. And hopefully I can get across that this is actually a very ambitious dream, but potentially, or maybe not potentially, it is doable in the future. And then, of course, like many good problems in physics, when you try to solve one problem, the tools are going to be applicable for a whole host of problems. Because this is really trying to solve a problem in quantum many-body theory, and in dynamics specifically. And so if your framework is sound, it shouldn't just work for fission, it should work for collisions, it should work for, say, quantized vortices interacting in a neutron star, and a whole host of other phenomena. All right, so maybe this is the most important slide in the talk. Just roughly, what is fission? What's the history behind it? So in 1938, it was discovered by Otto Hahn and Fritz Strassmann. 1 month later, oh, is the microphone still working?
No, it's a dot here.
Oh, okay, I'll just try to project a bit more. So 1 month later, it was described by Lisa Meitner and Otto Fritz. Ideally, she probably should have won a Nobel Prize for this description, but it wasn't given. And this picture is broadly how you can think of fission. So the way that she described it is something known as the liquid drop model. And what is that? You treat the nucleus like a charged liquid drop. And it's a completely classical description. And surprisingly, for some things, it's actually relatively accurate. So if you want to get binding energies of nuclei, you can get them to within 5% accuracy, just treating the nucleus like a charged liquid drop. And for fission, it can give you the big idea of why fission happens. So what this picture shows is beta. That's the deformation parameter. So basically how stretched your nucleus is. Because during fission, you have some tight compound system. It stretches and then it splits eventually. And B is your potential energy. And what you see during fission, so if you look at this dashed line here, this was the picture they had in 1939. So you have two main things happening. You have, yep.
I propose we take the microphone off. If there's any super you can see that.
Okay.
Thank you. Sorry.
Oh, no, it's a good idea. So there's basically two things happening. So first, if you take a compact object, and something that's known in nuclear physics is the nucleus is roughly an incompressible fluid, so its volume is going to be preserved as it stretches. So if I take an object that has protons, which are positive charge carrying particles, if I compress them, then the Coulomb force is going to be bigger. Protons don't want to be close to each other because they all have the same charge. So as the nucleus stretches, the Coulomb force dies out because your protons are getting further away from each other. But at the same time, your surface tension, which is minimized for a sphere, and maximized as you go to more exotic shapes, increases. So this double hump feature that you see, I mean, this single hump feature you see here is a competition between the surface tension increasing and the Coulomb force decreasing. And the key idea in fission is once you get past a certain point, so once your nucleus elongates past a certain point, it's just going to run away because of the Coulomb force, and it's going to keep deforming until it eventually splits. And these two forces are the basic reason why fission happens. The actual picture is more complicated because of shell effects. Your nucleus could be more stable at different deformations. And so you have the real picture actually has a second hump because of quantum mechanics. The real picture is much more complicated. So just in quick terms, fission, there's many different ways in which you can induce fission. So you can have a compound system in which a neutron is absorbed, a photon, a proton, and then it eventually splits. You can have, because it's quantum mechanics, spontaneous fission. So if you imagine you start at your ground state, you can just tunnel to the point of no return and split. And then after you split, there's radiation, so the emission of neutrons, the emission of gammas, and a bunch of different things can happen. The key idea for us is all of the different stages of fission, and this is why it's very complicated, look very differently from one another and occur at vastly different timescales. So if you want to model, for example, the change up from a compound system to two fragments, it's going to occur at 10 to the minus 21 seconds. But if you want to look at spontaneous fission, it can happen between 10 to the minus 12 seconds up to 10 to the 18 seconds. So in order to get one theory that can describe everything is very difficult for specifically this reason. And another point here is not everything can be measured experimentally in fission. So specifically this middle process, when you go from some compound system into two fragments, that part occurs too fast to be measured experimentally. But what happens at that stage does control the subsequent emission of radiation from the fragments, which is measured experimentally. And so that's why theorists like us try to model this intermediate stage. And that's going to be the focus of this talk. Any questions so far? All right. Right now, a much more, you guys have heard of current correlations in nuclei before, but this is extremely important for fission. It's fundamental. It's one of the newer things they started to understand more in the 70s and 80s. So what is paired? So much like in a superconductor, you have Cooper pairs. In nuclei, you also have paired states of nucleons. And it turns out, and you can solve this problem at a pencil and paper. It might be difficult if it shows up in an exam, but if it's outside and you can use Google, it's not too bad. If you consider any short range two nucleon attractive force, that force is going to have a minimum solution for nucleons with opposite angular momenta. For technical reasons, it has to do with how the orbital component looks like. And much like in a superconductor, this leads to superfluidity in the nucleus below the critical temperature. So nuclei are superfluids. And now I'm going to try to explain why current correlations are important to fission and how that relates to time-dependent approaches. So this is actually an argument from the 50s that they made more modern, I think, in the 80s. So the simplest approximation for a nuclei is you can just treat it as a 3D infinite square wall. And why is that? Because it's a bound system. And you know, since a nuclei is an incompressible fluid, the volume is going to be preserved. So during fission, as you elongate the system, one of the sides has to increase, and then the other two sides have to decrease, proportionally in a way to make sure the volume is preserved. Over here, you have your energy levels of the 3D infinite square wall without the units because it would be distracting, where Lx, Ly, Lz are the lengths of your box, and Nx, Ny, and Z are the three quantum numbers associated with it. So, does the pointer work? Yes. Okay, so if you look at this top picture, here you can see the energy levels of this equation here represented. So you have some degeneracy. For example, if Nx is 1, and then Ny and Z are 0, or Ny is 1, and Nx and Nz are 0, and vice versa. Now, what happens if I make some of these lengths longer and some of them shorter? What happens is certain levels are going to move up and certain levels are going to move down. And eventually, you're going to end up in a situation where levels cross. And this is very similar to what you'll see if you look at a nucleus while it's deforming and you look at the shell structure of a nucleus. So levels go up, levels go down. And when you see two levels meet, if you have an effective mechanism to jump to the lowest energy level, so say you're in a level that's going up, and you can make the transition to the level going down, then, because energy is conserved, then you have an effective mechanism to deform the system. And pairing turns out to be that important mechanism because it pairs your two fermion states into something that looks like a composite boson. So you get an enhancement at transitions. So this is just a technical term, Bose enhancement. If you look at the transition factor for bosons, it turns out to always be enhanced relative to fermions. And so if you have a good description of pairing, you can always stay at the lowest energy and you can effectively transition to a state that can split up. And the key difference between the different variations of TDDFT is how they treat pairing correlations. All right, a little bit more motivation before I present some physics. So why do we do DFT? Well, ideally, you can write down the many-body Schrodinger equation. You can write it down for some interaction that you know of, and you can try to solve it on the lattice, for example, solve it numerically. So let's consider uranium-236 on a kind of modest 30-point lattice in every direction. In order to represent the many-body wave function, you will end up needing 3 times 10 to the 708 complex numbers. So you're never going to have access to that object. You're never going to be able to directly solve the many-body Schrodinger equation. So what do you have to do? Well, quantum many-body theory really becomes a game of, can you approximate the wave function so you still get all of its essential features and correlations? But so it's actually solvable within using computers or supercomputers or whatever tool you have at your disposal. And so one of those approximations, and there's many models depending on what systems you're looking at, but specifically for heavy nuclei and dynamics, DFT is the main thing that I've seen be used at low energies. And DFT is kind of a remarkable theory. So people associated with it have won the Nobel Prize before, not Hohenberg, who was one of the original people of DFT, but Kohn and Sham won Nobel Prizes in chemistry for this. And basically the big, and this is a completely mathematical term, so it's an exact term. It says that huge object, that many body wave function, there's a bijective map between that and the one body density. So that thing that you need an insane amount of complex numbers to represent, you can represent by the number of points in your lattice, 30 cube real numbers. So it turns out this is easy to prove. It probably takes one sheet of paper. It's very straightforward. But they don't actually tell you how do you get the density. So there's still some approximations you need to make to have a prescription to get a somewhat decent density. And these two people, Cohn and Sham, introduced a practical method to actually get the solution for a DFT equation. And the only thing I would say here is they use mean field theory. So you go from a picture where you consider all particles and all possible interactions between them to treating them as independent particles interacting in a average potential created by the rest of the particles. And this is the big approximation made in DFT. Any questions so far? Yep.
Yeah, so to clarify, the approximation comes in when you're operating on these one body densities and not from finding the one body densities corresponding to the many body wave function itself.
Yeah, so all of the approximation is how you actually obtain the densities.
Okay.
So it's funny because you actually have to make a guess of what the many body wave function is to do DFT. And you guess it's a Slater determinant, which is just a product of independent wave functions for each particle. And because it's a fermionic system, you have to anti-symmetrize it. And a determinant is the best way to anti-symmetrize a bunch of functions. All right, so I think I'm gonna go ahead and skip a little bit. So this is just some technical details about how specifically DFT looks for nuclei. I told you before you need one density. I lied a bit. You need 12 densities, but it's still relatively cheap. Just a small note, there's many different types of DFT that you can use. Probably maybe some terms you've heard before, maybe not. Hartree-Fock plus BCS, adiabatic HFB or time-dependent HFB. And the only difference between these various treatments is how they treat current correlations. So the thing I described before, and how expensive they are to implement. So starting from the top, it's cheapest, and the bottom is the most expensive. And this is the one we use, and I'll try to justify shortly. And one more thing, specifically for TD-HFB, which is the most sophisticated treatment of current correlations in DFT, it's actually very expensive to do. So I don't know if you guys know too much about supercomputers and such. Some of you do. I see some head shaking. So basically all of the work has to be done in supercomputers. And for some studies we've done, we've had to use all of Summit or Sierra, which is a corresponding computer, for 12 hours. So while I was a graduate student, some of these simulations were actually the largest computer simulations performed at the time. And we've done something similar. So Frontier is the current rank 1 supercomputer. We've done something similar with it, but just using plane waves to test that the code works correctly. And it's not just for show. There's actually some good reasons for fission, why you need to work in such a large space. All right, now we'll get to the main results of this talk. So basically, I'm going to talk about what a group in the University of Washington did concerning this subject. Not too much work outside of that group. And I'm gonna go ahead and start from before my time. So this was done in 2016. And basically, if you look here, this plot is something known as a potential energy surface. So if you remember in the very beginning, I showed you those two humps, and if you get past a certain point, then you fission. In actual fission, you don't just elongate the system, you can have something known as an octupole deformation. And an octupole deformation is an asymmetry between the, I guess, left half of your space and right half of your space. So this is why fission isn't always symmetric. You don't always fission into two nuclei that have equal numbers of protons and neutrons. You can have one that has way more protons and neutrons and one that has way less. So that asymmetry is captured in the y-axis. In the x-axis, you have the typical elongation, and then you have your energy starting from the ground state. So, okay, you absorb a neutron, you get past this point here. So this is known as the saddle point, and at that point, the energy keeps decreasing, so your system is going to split. And you can see in most cases, it goes into the asymmetric region. So typically in fission, you're going to have fragments that have different masses. In 2016, for the first time, people were able to get fission within a microscopic framework using initial conditions. I mean, realistic initial conditions. So what do I mean by this? Before this point, if you didn't do TDHFB, but you used another DFT, you would either need an insane amount of excitation energy, so something like 200 MeV, when fission can occur at a few keV, so maybe 5 orders of magnitude more excitation energy than what is realistic. Or you would need to have the nucleus extremely elongated to begin with. So then when you start to run your simulation, it's guaranteed to split. So instead of starting right at the transition point, you start with a way more stretched out nucleus. But it turns out if you do HFB, which has a correct treatment of current, then you can start at the saddle point and you can watch it really evolve from a compound system into two fragments. And one key thing that was revealed is that the process is not adiabatic. And maybe I'll come back to this point, but for now I'll go ahead and skip it. But this is probably in all of the studies we've done over the years, this is the biggest point that we've found. And so you might call to question why I'm skipping it, because there's other interesting things to discuss. All right, so remember the big idea in fission is we want to be able to describe all observables eventually. One of those observables is something known as fission fragment spins. So these are quantum mechanical objects. So that means that your fragments are going to have angular momenta. And something that wasn't understood is how do you generate spins in fission? So in the 60s and 70s, so you guys are probably mostly in nuclear theory, nuclear experiment. Something you'll notice a lot in the field is there are a lot of old results, and then there's kind of a blank period for many topics, and then a revival. And this has to do with just how the government funds things, and for a while fission was important, less important, and now maybe it's becoming important again. So this was a very active topic in the 60s and 70s. And then by some strange coincidence in 2021, a bunch of groups published in the topic. And being one of these groups, I can promise you it was independent. People did not know that other groups were deciding to look at this, but by strange coincidence, maybe 4 or 5 groups published in the same topic after abandoning it for many decades. And as a result of that, there was a really big workshop held at the University of Washington in 2022. And the key insights that we learned that people hadn't known before or hadn't cemented before, maybe some people had ideas that this was true, was the fission fragment angular momenta are uncorrelated. Their magnitudes are uncorrelated. So if you measure, say, when you split your nucleus into two, if you measure one of the fragments and its angular momenta, you have no idea what the other one is going to be, which is a bit of a surprising discovery. And this is both experimentally and theoretically true. Everyone agrees on this right now. We also learned that neutrons are expected to remove a significant amount of angular momenta. So, like I said, eventually your fragments decay, emit neutrons and gammas as they start to de-excite, because they have a lot of excitation energy after fission. And people have previously thought neutrons maybe remove 1/2 of a h-bar of angular momenta. But it turns out that they remove significantly more. And we learned that the Coulomb torque between fragments can generate a lot of angular momenta. So if you have fission where the split, say these are your two fragments, is something like this. In principle, since there's a Coulomb repulsion between them and they're extended objects, maybe the Coulomb torque can induce a bit of angular momenta. So here are the papers published around this time. So it's quite a lot from a variety of groups. But something really interesting, which sometimes happens in the community, is you get a big disagreement. So, and sometimes that disagreement can actually be rather pronounced. So what I'm showing here is the angle between the angular momenta vectors. And I'm going to show you two different predictions. So one made by our group, which is all of these points here. So this is just the probability to measure the angle between the two fission vectors, normalized to some strange number. So if you sum it, you're not going to get 100%. And then this blue line is a different prediction by another theory group. So you can see they're completely at odds with one another, completely different. And what's the interpretation of both these? Well, the blue group, maybe that's not the best name, but their model is called Freya. So Freya makes the prediction that your two angular momenta vectors are going to be always perpendicular to the axis of fission. So basically, they're going to look like two random vectors in a 2D plane. And the prediction we made is they look like two random vectors in a 3D plane. So completely different. So if you take two random vectors in 3D, you'll get something that looks more symmetric. But because of quantum mechanics, it's used in one direction. It's not clear who's right yet. Well, I can tell you, our original prediction was not correct, but we have a new prediction, which is still different. So here in this plot, you can see the different prediction made by us. It looks more similar to what Freya is predicting, but still, there are some noticeable differences close to the ends. And there's significantly more structure here. The key distinction is if you look at this plot here, K is just the projection of the fission fragment's angular momenta on the fission axis. So if K is 0, that means that angular momenta is always perpendicular to the fission axis. And if it's non-zero, it means it's not perpendicular. It's at some off angle. So for various reasons, we were able to do a much more accurate projection. It required some technical developments because this calculation was already extremely expensive. But because of improvements in the theory itself, we were able to do the the correct thing, which we hadn't done before. And what we found out is it's probably best described as 2.5D in character. And what do I mean by that? I mean, the probability to have a projection of 0, so be perpendicular to the fission axis, is the most dominant one. But there's still a significant probability to point parallel to the fission axis, for angular momentum to point parallel to the fission axis. And so this is our prediction, and this is a paper published by a collaborator, which tries to explain the differences between this new prediction and Dry's prediction and our old prediction. So what you see here is 3 different plots. In the bottom one, so h bar equals 0 is the classical limit. So that's if you ignore quantum mechanics entirely and you just treat the angular momenta as classical angular momenta. The red one is the quantum limit. So that is if you include quantum mechanics and you have 2 vectors, but you don't know anything about fission, about the neck dynamics, none of that. This bottom is if you treat 2 vectors as 3D, so you unrestrict them, they can point in any direction, 2 random vectors in 3D, classical versus quantum. This middle one, this top one here, is if you treat them as 2D. And this middle one is our results, the red lines. So basically the claim we make is, and presumably this is a little bit biased because I'm arguing for one group, but you could not get Fry's result if you include quantum mechanics, no matter what you do. This is shown here. You take a 2D distribution and the quantum mechanics selection rules for angular momenta, and you see you get something more similar to what we're predicting than Fry's flat line. But it's important to note we also do make a prediction that there is going to be a significant component that is 3D. So, all right, now we're, yep.
So from my understanding, the prior predictions, what they do is they sort of do like a classical calculation of the rates of these different modes of, and then they show that modes that have angular momentum outside of the plane, the fission axis, are suppressed compared to ones that do, and that's why they neglect them. Is that the right interpretation? And can you then calculate like some sort of effective rate of those modes from TDFT and compare them to the classical picture and see if they line up, which they wouldn't presumably.
Yeah, so that's a good question. So I gave you the geometric interpretation, but there's a second interpretation that's in terms of collective angular momentum modes. And so this is basically, as your nucleus splits, there are eigenmodes of the system where you can have, say, if you see this is the 2 nuclei, you can have the angular momenta oscillate out of phase, but be perpendicular to the fission axis. You can have them oscillate in phase. You can have them oscillate out of phase parallel to the fission axis, or you can have them oscillate in phase. And in principle, you can decompose the system based on how much of it is doing various oscillations. And there's a difference between what Fryer predicts for these oscillations and what we predict. But I think the original paper they published, they didn't think of it too much in terms of these modes. This was after the workshop, and this became a more big topic of discussion. Then they published a second paper where they looked at the various modes and how they relax and which ones would be important. But we do make, obviously, because we predict out the plane motion, we make a different prediction and what modes are going to be relevant. And we could extract them from our simulations. Maybe we should have, but we were a bit lazy to do so at the time. All right, I think I'm gonna just cover one more topic. So the idea of scission neutrons, because this is a more recent thing we've done. And this is really a good example because you can actually do another popular way to do fission is you do it as a strictly static calculation. And this might be a bit surprising. Why can you do something that's dynamical and treat it as a static problem? There's actually, this happens many times in quantum mechanics, depending on how the system relaxes, what are the timescales, depending on what approximations you're making, you can many times model time-dependent phenomena as static phenomena. And this is an example of something that you can only really get if you do a time-dependent approach. So that's why I'm listing it here. And this also has a surprising history. Surprisingly, I mean, right when fission was discovered, they made a bunch of predictions that may actually turn out to be accurate, using far less sophisticated models than what you have today. And Bohr and Wheeler in 1939 predicted that when your nucleus splits up, it's possible it's going to end up emitting particles during the breakup. That's different from the opposing point of view, which is the nucleus splits up. The two fragments travel a long, long time until they don't feel the Coulomb force between them. And then much later, they end up emitting neutrons and gammas. So these are the two competing point of views. Surprising if you read the literature in this topic, it keeps flip-flopping back and forth. In the 50s and 60s, people were like, yeah, these probably exist based on some simple theoretical calculations. There was more skepticism later on, and they say, and now the predictions range anywhere from you're going to have 0 scission neutrons emitted to maybe 50% of all neutrons emitted are scission neutrons. So it bounces, depending on who you talk to, a wide deal. And who's correct? I'm not sure. Maybe experimentally they'll be able to determine the difference, but even experimentally, this is a really challenging phenomena to probe. But we decided, hey, let's use TDDFT and let's see what we see. Maybe we see them, maybe we don't, and make our own prediction in the topic. And this is a simulation. So this is not starting from the beginning where you have a compound system, because it's just boring frames if I include those, but starting close to when the neck ruptures, which is what we call scission, when the nucleus splits into two. And this is in log scale. And what you see is originally you have a nucleus. It reaches scission, the point of the neck rupture. And as it ruptures, you have clouds of neutron density being emitted perpendicular to the fission axis and parallel to the fission axis. And as you keep going, those clouds keep expanding and keep leaving the nucleus. So this was actually the extremely expensive fission calculations we had to do that required the full use of Summit and Sierra. And it's because you can see very quickly the clouds reach the end of the lattice, which is periodic, and start to interfere with each other. So if you don't have a big enough box, you're not going to see anything. And in fact, in principle, if they give us the time to do so, we should even consider bigger boxes on Frontier. And Frontier will, oh yeah.
I'm wondering how much can you trust the description at very low densities in TDDFT where you're looking at like almost a free single particle wave function?
That is a good question, because in principle, if the TDDFT we used was exact, you would see, so if you had the exact many-body wave function, you'd either see 1 neutron emitted or no neutrons emitted, or maybe 2 neutrons emitted. But actually, these clouds, if you integrate the amount of the neutron density in these clouds, you get maybe 0.1, 0.2. And our interpretation of that is you have a 10% probability to emit a neutron. That interpretation is shaky. It could turn out, like we said, it could just be, this is a fault of DFT. But it could be, it's mean field theory. This is the most likely thing to happen. That's what mean field theory gives you. That most likely 10% of the times you'll see a neutron. Yeah.
Can this help you then in determining the orbital momenta of the fragments? From the simulation, do you get do you only get these, or do you only get the densities, or do you also get the orbital momenta?
No, it's a good question. So right now we only care about the density, so the number, and the kinetic properties. We could also get the angular properties, but the big issue with that is our boxes are not large enough. So the interference occurs too quickly for us to make a prediction of the angular properties. In principle, if we do get time to actually go to much larger lattices, we could start to look at this. All right, so I think I'm gonna go ahead and
Sorry, can you say anything about what energies scission neutrons might be expected to?
yeah, so we predict them. Typical neutrons are maybe between 1 and 2 MeV. We predict the scission neutrons will be 2 to 3 MeV, so kind of close. But the bigger prediction we make is that sometimes, in rare instances, you'll get neutrons emitted at very high energies. And this is one possibility of something they could detect experimentally. Because if you actually look at the signal of scission neutrons and compare it to the typical hypothesis, which is you have no scission neutrons and they're emitted much later, the neutrons emitted parallel to the fission axis have the same type of signal. And that's what makes it very hard to discern experimentally. But it would be nice if you can find these, because since they are emitted at the neck rupture, they can tell you something about the neck dynamics, which cannot be probed directly by experiment. So this could be an indirect probe of a part of the fission process that you couldn't understand otherwise experimentally. I think I'm gonna go ahead and maybe talk about just one of the numerical studies we did, because it's a bit of a deviating topic. So it might show you some of the other interesting things you can do in TDDFT. And I guess I'll go ahead and discuss this topic, and this will be my final thing. So I'll let you guys go to lunch and make us all happier, I'm sure. So from the very start, when I discussed the Hohenberg-Kohn theorem, I told you DFT should be equivalent to Schrodinger's equation. But because of practical limitations, we're not sure if our representation is actually equivalent. In fact, almost certainly it isn't. And so one question is, how good is it, basically? And one test of that is you can look at something known as quantum chaos. And so here's the big idea behind it. Schrodinger's equation is linear. So what that means is if I find a time-dependent trajectory using the time-dependent Schrodinger equation, and then I start a second trajectory with a small initial perturbation, you'd expect the evolution of those two trajectories to be parallel. If you have a chaotic system, the only thing that means is you start with some initial condition and you introduce a small perturbation, and the two trajectories will diverge from each other. So we want to see TDDFT, which is represented by a set of nonlinear equations on the surface. Is it actually equivalent to Schrodinger's equation? And one measure is something known as the Lagrange exponent. So you can take the difference between your two trajectories. It's going to be proportional to some exponent e to the lambda t. If lambda is positive, you have chaos. If lambda is 0, then you have a linear description. And if lambda is negative, then you actually have a restorative theory, where you start with two different initial conditions, but they converge to the same trajectory. And we looked at this for both fission and collisions, and we plotted it here as a function of time. And what you see is that long times, it's slightly positive. Both for, I guess for collisions, it's unclear, but for fission, certainly. We even looked at quantized vortices, and we saw the same feature. And so what's our conclusion of this study? Does TDDFT lead to chaotic trajectories? Well, the Lagrange exponent is positive, so we say no, it doesn't. And why do we say that? Because the time scale relevant for the systems of interest, so fission, as the nucleus splits up, or collisions, you collide and then your two nuclei fuse or separate. Within that time scale, it's not going to make a difference. But in principle, this does indicate that there is something missing in DFT in current implementations, because you'd want this to be 0. And what could that be? It could be memory effects. And what do I mean by this is if you do the time-dependent Schrodinger equation, you know, if your Hamiltonian at different times doesn't compute with each other, you have to use a far more complicated description. It could be something like that. Or it could be the approximation we're making to the many-body wave function is not correct. Yeah.
So, at what point does that like, what is the scale in which that exponent you can just go like, oh yeah, that's like, you kind of did that there, but like, yeah, at what point does it become like we can? It's so close to 0, we don't have to worry. It is 0.
So we do have something known as this MSS val. And what this is this guy here, who's extremely famous in the string theory community. He basically said this is the upper limit for chaos in quantum systems. And so what we did here is we know what the temperature is because we have fragments that have excitation energy, and you can approximately correlate the excitation energy with the temperature. And we make the claim that it's not relevant because we're far below this maximum bound. Is that a reasonable thing to state? Maybe not. But another way to look at it is you can actually look at the observables you get at the end of your calculation, and you can see they differ by 1% at most. So if you look at the fragments, masses, charges, kinetic energies, excitation energies, they're so similar that we say, okay, for a bit of noise, you're going to get some error, but it's not going to actually make a difference. Yep. All right, some concluding. Any?
Maybe we'll wait for him to finish and then
So I think for some concluding remarks, I'll just reemphasize the main point in fission theory. So the main thing is for this problem that's 86 years old, we eventually want to have a complete microscopic description. And this is actually a bit remarkable in quantum many-body theory, because oftentimes you'll see a phenomena and people will be able to find a framework within a relatively shorter period of time. But fission, for the various complexities mentioned above, is one of those problems that just seems very difficult to get a solution for. So for comparison, superconductivity, which I think was discovered in 1911, got a microscopic theory in I think was 56 or 46. maybe 56, 57, 46 years later, known as the BCS theory. So this is the key thing. Can we have one consistent framework that can describe fission, and it remains to be seen? But we're trying to make steps in that direction. Many people are trying to. All right, that's it. Thank you very much.
Questions? Yeah, Patrick.
On the spin correlation slide, what's going on with the spike you guys have at around 20 degrees? Yeah. All of your plots seem to have 20 to 30 degrees from big spike above.
Yeah, this has to do with the Clebsch-Gordon coefficients. So I don't know if you guys have heard that term before. Okay, I see some head shaking. If you just take two vectors and then you try to calculate the opening angle between them, say, let's look here where you even ignore, because you see it in all of these simpler ideas, as long as you include quantum mechanics. It turns out quantum mechanics surprisingly forbids your two vectors from ever pointing parallel. And why is that? I don't have a good physical reason other than if you just do the projection. So if you just take two vectors, you include the Clebsch-Gordon coefficients, then you'll see this is a quantum mechanically forbidden region. And why the spike at 20 to 40 degrees? I wish I had a better explanation, but it follows along similar lines where if you do the projection, then you see this big spike. But what is the reason outside of quantum mechanics and the selection rules? I'm not too sure.
Earlier you mentioned Coulomb torque as possible contribution to the momentum after the fission. Could you explain that one more time briefly? Then I think I have a question.
Oh, sure. So let me go all the way back here. So in the way that we do simulation, since we don't include fluctuations, you wouldn't have any Coulomb torque. The system is just going to split up into two. But if you had fluctuations and your neck was not always splitting perpendicular to the fission axis, so instead of this situation, maybe you have this type of situation or this type of situation, then what happens is you have extended objects. So let's say you split this way, and then they're spinning because of the rupture, but because of the Coulomb force between them, that can impart an additional amount of rotation or an additional amount of angular momentum.
Okay, I might have a silly model in my head or like a silly way of thinking about it, but Coulomb force was traditionally a central force, like it could apply angular momentum. So why does it do it here?
So in this picture, it couldn't, but if you have extended objects and you have them off angle, so for example, consider instead of this orientation, you have the nucleus splits, and it splits this way. At this point, you could actually exert a torque between the two objects, and you can do this either in a much simpler DFT. So the people who made this claim actually used Hartree-Fock, and they didn't even consider fission. They just put two nuclei that have deformations. They're not spherical, and they put them next to each other, and then they saw what happens, and then they saw that it ends up rotating because of Coulomb. Yep.
Okay. I have a different question about the scission neutrons, or on the slide with the scission neutrons.
Oh,
the DFT prediction includes the prompt neutrons from each of the fragments, right? Not the neutrons. Can you, is there a way to validate the predictions of this neutron emission by looking at the prompt neutrons are measured? Do your prompt neutrons look like the ones that are seen in experiments?
So they are, which is why this prediction is a bit difficult to validate. So prompt neutrons, for people who don't know, these are just neutrons that are going to be emitted after fission. And these actually include the neutrons as the fission fragments start to de-excite. Not the ones much, much later, but most neutrons emitted are prompt neutrons. So they could include the ones after they're fully separated that experimentalists and a lot of people agree do exist. In fact, everyone agrees those exist. Just what portion of those come at the rupture versus much later, that's a debated topic. And the short answer is there probably is some experimental signal, but because they actually look kind of similar, the two signals, whether you include scission neutrons or you don't, because it's a 10% effect, and where they're emitted and their speeds and their directions are not too different, you'd have to do a very precise experiment to distinguish between them. And at some point, and actually it's my fault because I was the one responsible for making the prediction between the differences of the two models. And then you can see experimentally, can you find it or what sensitivity? I just haven't had time to do that, but it should be doable. And I'm not sure right now how big of a difference there will be for stuff they actually can measure.
Okay, I have time for just one quick question, maybe, since I will really ask many questions. I'm gonna
On the slide, what do you mean by transformation canonical basis?
So the canonical basis, for various technical reasons, turns out to be the most efficient basis for representing your system. So it's just, you have a collection of wave functions, you do some transformation, and then you get a second collection of wave functions. And you're always allowed to do this in quantum mechanics as long as you use a unitary operator to do that transformation. And so it turns out if you, say like if you have 1 million wave functions, single particle wave functions, and if you calculate the total number of particles, if you go to the canonical basis, you can keep 100 wave functions and reproduce the total number very accurately. If you work in different bases, maybe you need 1,000 or 2,000. So it's just an efficient basis for making truncations, which means you can do projections, for example, that couldn't be done previously.
Great. We have one question in Zoom. Everyone, if you need to go, please go ahead.
Feel free to go. Romualdo, you can ask your question.
Hi. Since the scission neutrons are so hard to measure, does ternary fission give you the same access to the neck dynamics that the scission neutrons do?
Yes, it should. And actually in this paper, which I conveniently left out, we do make some predictions for charged particle emission as well. Just the probabilities that we're predicting for scission, I guess for ternary fission, is much lower than what we predict for scission neutrons. But yeah, in principle, I mean, for sure. If, as far as I understand, in fact, ternary fission, as far as alphas, a lot of people do believe that they are emitted at the neck rupture. So it would definitely be a good probe experimentally.
Thanks. Great.
Okay, well, thank you, Brian, again. Here today and tomorrow, if you would like to meet with him, we want to